Hello everyone, thanks for being here. We recently adopted Iceberg into our data platform and then we got huge benefit. Today we are going to share that journey with you. First we'll talk about branch, data and data platform architecture, and then why we needed Iceberg, how did we implement Iceberg into our data platform, and then what is the architecture looks like after adopting Iceberg. Part of this project we developed few tools, we'll go over detail. And finally, we briefly go over about the benefits we got from this adoption. About Branch, Branch provides mobile linking and measurement platform. It's widely adopted, more than 100K apps using since it started. Few metrics that will help you to visualize our data platform scale. So we get 40 billion events from the mobile, and then 100 terabyte data will ingest into data lake daily. Then we have more than 500 Hive tables. Overall, the data lake size is 10 petabyte. Then we have batch and streaming jobs running in our data platform, and that we have mixed low latency queries and then Presto ad hoc queries. These are the system we use in our data infrastructure. We use Kafka to pass the messages between the pipelines or between the systems. And for compute, we use Flink for streaming. For batch, to process the data in the batch, we use the Apache Spark. All the data are stored in S3. In Parquet format, we use the Hive as a catalog. In terms of query engine, we use the Druid for aggregated low latency queries, and then Trino for ad hoc to query the raw data. And then we use Apache Airflow to schedule the jobs, and then everything runs on Kubernetes. This is our existing data platform architecture before adopting Iceberg. So the microservices will send the data to Kafka in protobuf format. To ingest the data into data lake, we have two-stage streaming pipeline. The first stage will take this protobuf data and put it into Avro, and then the batch will come that will convert Avro to Parquet. So the Parquet is stored for long retention. The users will query or data product will query from this Parquet data. This Parquet data registered to the Hive metastore as a external table. The Presto is connected to the Hive catalog. So if you want to query the data in raw format, we use the Presto. And then we also aggregate the data that will send to the Druid. So the dashboard, low latency dashboard, everything will use query from the Druid. And finally, we have a couple of data consumer. One of them, we have a couple of data product that build on top of the data, internal BA tools, and then external customer facing dashboard, and then interactive queries from the users. You might be asking, the existing architecture itself scalable, then why we need Iceberg? Let's see. The major challenge we had with existing architecture, mutability and query performance. What the challenge we had with mutability, we could not change the data safely. If we want to change any data, we have to rewrite entire partition. The rewriting partition, first we have to delete it and then write it. Those are two separate transactions. During that, the customer can see the empty data. The second issue we had with mutability, changing any data takes more time. So one of the major use case, if customer asked to delete the data from our data lake, for us it took more than a few weeks. The second challenge is query performance. Our raw data is huge. The only data optimization we had, partition filter. We partition the data but hourly. That is not good enough for all the use cases. To overcome these two challenges, we started to put solution like copy the data to improve the query speed, and then down the line we got our system become complex. We could not evolve as a platform. So we are looking how to solve these two problems at the platform level, and that's when Iceberg came into the picture. Iceberg natively supports update with the consistency that solves our mutability problem. And also, if we group the data together, we can delete single customer data without rewriting entire table. In terms of query performance, we thought we can range sort by customer ID, and then query performance will be improved. It's because Iceberg store the column metrics in the metadata. One of the column metrics is lower bound, upper bound of the each column. So when the query comes with the tenant ID filter, the query engine will look into the Iceberg metadata and then see and then pick only the relevant file for that particular query. So we know now why we selected the Iceberg. Let's see how we integrated Iceberg into our data platform. Yeah, the very first thing we did, we also looked at other open table format like Hoodie and Delta, and then finally we selected the Iceberg. It's mainly the Iceberg fits our ecosystem very well and then solves our the core problems. Next, we need to select the catalog, whether Hive catalog or REST catalog. We went with Hive catalog because we already running the Hive, and also we don't want to introduce more changes part of this migration. The next, we have to prepare our environment to support Iceberg. Whatever the system that touches the Iceberg, touches the data, should know how to parse the Iceberg format. For that, we had to upgrade Spark 2 to Spark 3, Trino, EMR, Flink, everything we upgraded to latest to support latest version of the Iceberg. And then we added Iceberg library into this framework. And then finally, we configured the Iceberg catalog. One thing was useful in the Trino. We already using the Hive catalog. The Iceberg catalog is another one. There is a redirect feature in the Hive catalog where if it automatically redirects Iceberg table. If user queries the Hive catalog, if it is Iceberg table, then it will redirect to the Iceberg catalog. That was very useful. So now our environment is ready for Iceberg. We wanted to gain some production experience. For that, we took first small data set and then migrated into Iceberg and then observed how this system behaves. So now we ready for the major data migration. To migrate the Parquet, the large amount of data we had in the data lake, either we have two options. One, we can do it in place or parallel table creation. We went with the parallel table creation. It's because doing in place is riskier. All the customer data product is frequently querying this data. That's why we went with the parallel table creation. To migrate any Parquet table, first we start the double write. That means we launch the Avro to Iceberg pipeline that will copy the data from Avro to Iceberg. That will ingest the data continuously. And then we need to perform quality checks. We developed one quality check process that will compare Parquet and Iceberg. It will compare count, schema, and then data. If there is any discrepancy, it will output into this quality check result table. Now, finally, we need to copy all the historical Parquet data into Iceberg. For that, we created another process. It's a backfill process. That backfill process will launch Spark job per partition, which will copy the data from Parquet to Iceberg. Once backfill completed and then all the quality checks process, then the new table, Iceberg table, is ready for consumption. So then we will go ahead and then update all the consumer to point the Iceberg table. And then if all the consumer is updated, and then if there is no traffic in this old table, we just stop the old ingestion pipeline and then delete the data. Okay, so after implementing the Iceberg, this is our data platform architecture. I will call it its data lake house. It looks like data lake Iceberg data lake house on S3. So still the data stored in S3. The Iceberg has two table data. One is metadata and then actual data layer. The data layer is Parquet. So this Iceberg table registered into the Hive meta store as the external table. Hive just points to the latest version of the manifest file. So this is our raw event data, which we already saw how we migrated. And then we introduced another data set called analytical warehouse. This is mostly for to create our derived pipeline or internal KPI metrics, we use the dbt Spark to create internal metrics. So the analytical teams will submit the query in the Spark SQL, put it in the dbt model that will create the internal metrics. So now we have the mutable data lake and then analytical warehouse. Then still there is one piece of information is missing, which is our entity or app data, which is stored in different system like Postgres, Salesforce, and a couple of other building system. And there are some tail end. For that, to bring the data into our data lake, we introduced the Airbyte, which also another open source tool, which has connected to the system that pulls the data from here and then put it in Iceberg table format. So in the query engine or consumption side, there's no much change. That architecture are same as like before. It's accessed like any Hive table. And as part of this process, we develop a few tools. One of them is column metrics. We heavily use the column metrics here. Most of our table have 200 to 500 columns. By default, Iceberg picks first 100 columns to collect the column metrics. So we need to supply our own 100 columns. For that, to simplify that process, we created a YAML-based approach where the table owner will give the column 100 columns into the YAML file, and then we have the wrapper around Iceberg that will use this column metrics template and then whitelist into column metrics. And then next tool is disaster recovery. We need something for disaster recovery. For that, we created simple tool that it will go through all the Iceberg table, copy the metadata into another bucket frequently. And only for opt-in tables, we just copy the full data as well. And then finally, the main important process is a table maintainer. Andre is going to lead it. Andre, over to you.
Thanks so much. Hi, everyone. I'm working with Ramesh on this Iceberg journey. And now let's talk about something much less exciting, but still very important thing, which is table maintenance, metrics, and alerting. Next slide, please. Yeah. So let me go you through maintenance routines that we do right now for our tables and how actually Iceberg changed it, improved it, or add complexity. So first is data retention. Before Iceberg, as Ramesh said, we had Parquet LakeHouse. So we use combination of S3 lifecycle rules and custom jobs that just deleted files directly from S3. Right now, we cannot use lifecycle rules anymore, but Iceberg allows us to use a delete SQL statement, which actually I found much more convenient. It improved our code and it made it much easier to test. Next three, which is snapshot expiration, orphan files, cleanup, and data compaction, are part of Iceberg distribution. So it was easy to integrate. So let's go through them. Snapshot expiration one, it's something we have to do because of Iceberg. As I said, we use delete statement to delete data, but in reality, after you run the statement, it's just another snapshot that created. Data will be still sitting in S3. So only when you expire snapshot, data will be completely removed. Orphan file cleanup. It's another thing that we have to do because of Iceberg. As I mentioned, we cannot use S3 lifecycle rules anymore. But if any file is not connected to your data set, like someone accidentally put it, or we saw some leftover or failed job, this data will sit in forever. This is where this orphan file cleanup job actually comes to the rescue, because it allows you to remove any file that's not connected to your data. Data compaction, it's something we found useful for dbt use case, because sometimes it can create data set with a lot of small files, which can impact query performance. So now we just can rewrite same data, but with less files. And last one on this list is clean up temporary tables. So as engineers, we need to create temporary tables. And what I mean by this, it's actually normal tables, but that is not part of any process. So we need it for development, for debug purposes, for backfills. And the problem with those tables, people tend to forget about them, and I'm guilty as well. So with Iceberg metadata, we can very easily identify tables that were not updated, like no changes for X amount of days, so we can very safely drop them. Next slide, please. So in order to automate all of those tasks that I mentioned, we build a process. We call it actually table maintainer. I know it's not a very creative name. So let's take a look on configuration example. We have one config file per each schema, because we found that all tables under certain schema should be maintained in most cases same way. But as you can see, we can also add any override on table level. And in this config, we can enable maintainer as a whole, or we can enable, disable each job in particular, or tweak any parameters. Next slide. So this is how our maintainer process looks like. It consists of three major parts: scene configuration, then create maintenance task, and actually execute them. So in first step, what will happen? We will just fetch configurations, then we will just create configuration like merge defaults with table overrides, and push that to Iceberg table properties. And then next process, task creator, will just go through all tables that we have. It will read those properties and will generate task object and put it in a queue. And last step, this is where actually heavy lifting is happening. This job will fetch task from a queue and execute based on its type. And as a result of this, we will also have some metrics and details like whether it succeeded or failed. And for example, if it's snapshot expiration, we will see how many records or files were deleted, and so on. Monitoring. So here I'm going to cover metrics that we gather and alerts them. So in general, why we collect metrics? Because we really want to understand how our data changes over time. Another part, we want to see whether our table maintainer is working correctly. And also we want to create alerts if something goes wrong. So let's take a look at what metrics we actually gather. We have a three category. One is snapshot record level metrics. So every X number of hours, we collect what is the total records number, what is snapshot count, and what is important one, how many records were added and how many were deleted. It helps us to understand how data is growing over time, and also whether our table maintainer is really deleting the record. Because if we see 0 for this column, something is not right. File metrics. It's actually comparison between what files are really in use, like they connected to latest snapshot, and how many files and what size of data that we actually just keep. So for example, if this number of files is much bigger than that connected to latest snapshot, we probably need to run snapshot expiration more often. And partition metric is partition count, how many records per partition we have, and what is it changed to this count. We needed to understand whether we partition our data set right. Maybe we create too many small partitions, or vice versa. Yeah. And let's go to alerts. So right now, based on those metrics, we created three types of alerts. So first one is missing table alert. So it's fired in case when we cannot access table anymore, which was there previous time. It can happen because someone accidentally dropped it, or maybe data got corrupted or something else. So we really want to be alerted on this one. Second is abnormal table size reduction. We already have some idea how many records should be deleted by our maintainer process. But if it's more, like 20% of data got deleted, we want to be alerted as well, because maybe we have a bug in our system or someone accidentally deleted this data. And third one is unused table. In compared to a different process when we just delete temporary tables, this one is for real tables that we use for production processes. But sometimes when we duplicate something, people can forget to remove tables. Also, it can be that some process can fail for like a few days, and with this alert, we will know about this. Yeah, so that is it. Back to you, Ramesh.
Thanks, Andre. Let's see what improvement we got from this adoption. The overall, our data platform became more powerful, and also we are able to save some cost. So I listed four major improvements here. The first one is the change became more easier and safer. So we are able to update in place. That simplified our backfill process. So which resulted in a reduced backfill time. Another useful thing we had the snapshot. So if there is any data quality fix, the snapshot helps to compare what is the before and now. The ASAP queries are very powerful. We use heavily the ASAP queries. And the second thing is query performance. The most of our queries have a tenant ID filter. Those queries had 20x performance. It's because of we structure the data, we range sorted the data. That's why. And other queries which involves the column metrics are if naturally grouped together, those are the 20 to 50% reduction. It's mostly based on the filters. And if nothing, rest of the queries stayed same. The one good thing, query performance didn't go bad compared to Parquet. And then regarding the cost, one of the data product which used the tenant ID filter heavily saw 40% reduction. That is huge for us. Then in terms of the storage cost, we reduced 18%. It's mostly because we reduced the number of redundant data copies. And another one, we use AWS Intelligent Tier, which means if the file is not accessed for some X days, it will go to the cheaper storage. Since Iceberg has the efficient access on the file based on the query, we saw the number of increase files in the cheaper storage is high. So those reasons we saw the storage reduction cost. Finally, the productivity of the pipeline development also increased. We don't need to sync partition and the schema management much easier. Another major one is the merge query. We don't need to create the biggest to merge the job. We don't. It's simple merge SQL is good enough. And these are in our roadmap. There are few use cases we see. We have to bring the data in the real time into Iceberg table. We are looking at the Flink sync right now. On the next one, we use the Airflow here to schedule the jobs. In the Airflow in the scheduling orchestration layer, PySpark is very heavy. And we are looking something very small, lightweight that will check whether data is ready or some metadata checks. For that, we are planning to integrate by Iceberg. And then the REST catalog, which has more benefit. One of them for us, we're looking implement the fine-grained access control. And the last one, recently the Druid introduced reading the ingesting data directly from the Iceberg table. Again, we use Druid here. We are looking integrate that as well. Thanks everyone for staying with us.
Thank you, Ramesh, Andre. That was great. I appreciate it. We have a lot of good questions in the Q&A section, so I'll pick a few of these. You mentioned this as part of your future work, but it came up on your architecture slides about the original or the initial ingest from Kafka. So you're landing in Avro and S3. What streaming system are you using, technology are you using to do that? And why not directly to either Parquet or Iceberg? Why the hop into Avro?
Okay. Little bit history. We started the ingestion pipeline around 2018. So we first started to ingest directly from Kafka to Parquet. That has the problems we had because we need to convert row to column in memory. In the large scale, we cannot do it. That's why we converted into two-stage pipeline. First write into Avro. That helps to for speed up the write, and then bash just convert it into Avro to Parquet. So we use the Apache Flink. Now the reason we are looking Flink to Iceberg is for small data set where we need more update frequently. For that, we are looking Flink to direct ingestion. Still, we want to keep until we haven't experimented and we haven't tested with Flink Iceberg pipeline. Whether it's solved or not, we don't know. That's why we haven't used.
All right, and it's something you can tune into the streaming panel later today, and lots of experts on that subject.
Yeah.
Next question here is on your evaluation of Hoodie, Iceberg, and Delta. Can you share any more about your evaluation criteria?
So we looked at what works for our environment and what's the future direction. We are in AWS and we run our own data platform here. In that long term, we don't have any plan to move any other cloud or anything. That's why we didn't go with Delta. And then between Hoodie and Iceberg, we selected Iceberg. It's mostly because of the column metric. We like the column metrics in the Iceberg to speed up the query performance. That's our main reason.
Speaking of column metrics, another question is, you had this tool you built for specifying which columns to collect metrics on. How does that actually get leveraged by the Iceberg libraries? Can you speak any more about that?
So we take these column metrics from the YAML file, and then Iceberg, there is a properties for each table where we can whitelist Iceberg table. So we'll add these are the column whitelisted column metrics. So when the Iceberg ingests the data into the actual ETL, when we ingest the pipeline, it automatically calculate the column metrics and put it in the metadata.
So just using Iceberg table properties, you're saying?
Yeah, just table properties. We just we simplified, putting the Iceberg table property in easiest manner.
Great. The next question is about late arriving data and just you deal with late arriving data in the system.
Yeah, that's a good question. One thing we did, the moment we receive the data from the mobile, we put the timestamp. So everything for us, that is the timestamp we operate on everywhere. And so that's why we usually don't handle the late arriving data in our pipelines. So everything comes from the mobile on the real time, and then we just put ingest the timestamp on the gateway level. So all that data, everything operate on that. And there are very few pipelines we have later in data. For that, we could not use this architecture. We go with different architecture.
Two related questions here about optimization, compaction, and configuration related to that. Given your all scale, what recommendations do you have on how to configure your tables, how to do compaction? Has there been any performance impacts of running compaction, and any lessons learned there?
Andrew, you want to take it?
Yeah, as I mentioned, in most cases, we don't have any problem with our files. Only for few, like dbt1, when we don't really control how many files will be created. this is where it can be useful, but those data sets are small enough. So for us, we haven't seen any problem yet. So it's actually nothing more I can share.
Yeah, only doubt I had in the mind how the orphan file works. Is it going to delete some unwanted thing? Those are the doubts we had initially, but those are pretty much stable. We didn't see any issues so far. And another doubt we had whether it's concurrent, when the maintainer runs, whether ingestion any problem in the ingestion job. We use the Airflow to multiple retries, so we didn't get any failure. That retries is good enough to handle those conflicts.
Very good. There's a question here about, do you have any benchmarks, performance benchmarks? And you talked a little bit about this, but between the Hive system and the Iceberg system, any performance benchmarks you can share? And a corollary question, which is, Iceberg snapshots, you keep some amount of time travel and history, which has an impact on S3 costs. You're potentially storing more data, but you also mentioned S3 cost savings. So how do you think about the interplay there of sort of keeping history and versus saving on storage?
I think it depends on what you need. For us, we save we by default we store 7 days of data on all the tables. In terms of a cost reduction, we already have multiple copies of data before. So compared to that, this is not much big for us. Even after we could able to save it, the snapshot helps a lot in the cases. You can roll back easily, and then you can compare it. More than cost is, I look into the benefit, how much benefit you get from that, and then decide on that.
Makes sense. There's a question here about mutability and basically how much of your data is append only versus how much data actually requires updating. Because you mentioned being able to do more fine-grained updates was a big driver for you, moving to Iceberg. So
yeah. So
what's the mixture in your world?
Okay. By nature, our data is append only. It's a raw data, even stream. It's append only. For us, the problem comes when you want to touch the append only data for like GDPR, data quality fix correction. Those scenarios will come very frequently. We have to spend more time on those. So that's the main driver for us to mutability. It's kind of low mutability frequency. There are very few data set like entity data set. They will have more update, and the volume is not much over there. So we are able to update high frequently with a low one.
Okay. You mentioned there's some alerting you have built up around removing temporary tables or ones that have been receiving the updates recently, as well as being able to automatically clean up data. If data is accidentally deleted, does that ever happen that data is deleted and you need to get it back? And if so, like how do you get it back?
Andre?
Yeah, so we have backup mechanism. So we store metadata and data in a different bucket. And we already tested it. We have few tools that can bring this data back. And we tested multiple scenarios when like someone accidentally delete metadata, we can just easily bring this metadata back and it will work. If data is deleted, we can also bring it from our S3 location for backup.
And also we do this one only for wherever we ask the user manually create the schema. We separate the namespace. Few namespaces, the process creates the table. We don't enable this one. Only the namespaces the user created, creating the data manually, where we needed this feature. Even if the data lost in that, we haven't had the scenario, but even lost is a less impact.
Okay. I have a question which is related to the switching from Hive to Iceberg and how you do that without, did you achieve that without having any downtime for users? You mentioned, I think, some on the maybe Presto or Trino side, catalog configuration, but maybe talk a little bit more about how you achieved this migration and making it not painful for your downstream use cases.
Yeah, so we had the double write. The strategy we chose the double write. We create the parallel table. So the old table and the new table will be always up. So we just, in the process, we just put it in the new table and then release it. And then we give the notification to the customer, hey, these tables will be migrated to Iceberg, and then old one will be deleted after a certain point. So we did at the release level, and then paid some cost of writing double write.
Okay. Did that require any code changes from the downstream consumers, or they ultimately, as you were dual writing, but they somehow you swapped the namespaces or did table renames? How did you achieve that?
We went with different schema. It triggered the code update. So we had to update all the script, all the process, because we know this is a big migration. We preferred, we give the priority to the data quality compared to the some small disturbance to the customers.
Makes sense. Okay. Anybody else have any questions? You can also request to hop on video if you want to ask a question live. Make sure I don't have anybody waiting to ask questions live. Also, the poll is open, so yeah, please go to the poll before you check out and give us feedback on the session. Much appreciated. Anything else, Ramesh, Andre?
Thanks, Jason.
All right. Thanks, everybody.